All right, the challenge we're actually wrestling with is making a leak-tight seal in the calandria. And we're using a calandria tube insert to expand that calandria tube, forming the seal. The challenge that we've had to overcome is the roughness factor, and through our testing, we were trying to find methods to actually reduce the roughness to help us get a better seal, so that when you actually roll tight, there's no leak paths for air or the moderator water to leak out through. So that's the challenge we've faced.
So it's a leak smaller than the thickness of a hair. They're very hard to decipher. You'd have to tear it apart and look under with a high definition microscope to see these sort of leaks.
We've developed a method to actually roll and have a seal that when this is permanently deformed, it will stay deformed, and you'll have a seal that you don't need to worry about going back in 5 years and 10 years down the road to repair. So inside this tube, this would be up against the face, locking onto the inside of this tube sheet here. And the calandria tube, which you see here, will actually come in just a ways to about there. It will fall in probably the middle of that wide land of the insert. So we use a mandrel, which will go inside this tube, and it expands, which is going to continue to stretch this around the circumference and basically form a seal. So this diameter will be increased after we're done our joint to whatever we calculated the necessity to be to make our seal. We now, through testing various methods, have found a repeatable method. By reducing the roughness, we're able to get a good seal using our standard rolling method. So this here would be the final product. Earlier I demonstrated with the insert and the calandria tube. This here is now our insert. It's now mated to this is our calandria mock-up, our tube sheet. And the calandria tube here is firm inside. I can't move this, I can't twist this. And this is actually a pass joint that we have leak test. And it has met our criteria, so this method of polishing has proved to be promising at this point. And basically it's a big teamwork. Every time we provide these samples, they'll be tested, and then all that data will be analyzed by all of our engineering staff, and they'll develop our path forward. Do we continue to test this method? Is this acceptable, or do we start something new? It's a huge team effort.
We've got to make sure that what we do here is a mirror of what we can do on the face of the reactor. Well, for nuclear, safety is number one. The last thing you want is an issue. So we want to make sure that this is as leak tight as it can get to reduce problems. You want these reactors to run for another 30 years safely. So we want to ensure that those are leak tight for another 30 years.
This looks tight, it seems tight, and chances are if it was in a different purpose, this would be an acceptable joint. But we're dealing in the nuclear industry, and the standards are as high as they can be. So we can't have any doubt. So it's not just meeting our diameter. We have to prove that we know the method's repeatable. We have to have proof and documentation, and we do so through our leak testing methods to show on paper that this is our leak rate, this is below the acceptance criteria without a doubt. The standards are very high, but they're required when it comes to nuclear. Like, safety is the utmost importance, and then we have our quality, and we want to make sure we deliver on both.